previously I presented as an example of a context-free grammar, GP here, which I claim describes all palindromic strings or palindromes over the binary alphabet, meaning zeros and ones. So it's able to generate palindromes using these production rules. So I just claimed this, but I didn't prove it for you. Now, a key part of proving that a context-free grammar is correct or grammar is correct is using the appropriate definition for what the language it describes is, which we had this definition I introduced you to. So remember, we have our for tuple, variables, terminals, production rules, start symbol, and I wanted to know what the language of that grammar was. And it's simply all of those terminal strings or sentences that are derived, or if I start for the start symbol, it derives W if W is among terminal symbols, T star. So 0 more symbols of the terminal symbols, or terminals for short. So we're going to use this definition to prove that this context-free grammar is in fact correct. So let me give you the game plan, and then we're going to dig into this. And I like to make sure you see at least one example like this. So a common approach is just simply to use that definition I have over there. Because if my claim is it describes a given language, well, that's the language of a context-free grammar. So most certainly a common approach to doing this is to use that definition, right? So very often mathematical induction is your best friend. So very often you'll find that they use mathematical induction. I'm going to actually show you in this proof that there's actually at least a couple different ways you could use mathematical induction. So very often in our proofs we've been using different concepts, namely the length of the string is a very common one. We'll use that one in this proof, but I'm going to show you a different way is by applying derivations, or derivation rules or production rules. So how many times you apply a production rule. That's another thing you could perform induction over. So I'm going to show you how you could do that with this example. So our goal is to show that GP is in fact correct. So I'm just going to make sure that we have it sitting over here. At least it's production rules. That way you know and see where it is. So I got 0, A0, 1, A1, 1, 0, epsilon. I'm just going to put that over there. Just going to put a little note around that. That way we have that in front of us, because we have to make sure we account for this appropriately. So very often mathematical induction is used, and your goal very often when we try to do this is I would like to make sure I show, just like we've seen before when we try to prove the correctness of our models, is if I give you a string W, I want to say that it's in the language of that context-free grammar if and only if W is in the language that I'm interested in. So I want to show that this relationship exists. So there's two parts or two directions to such a proof, because it's an if and only if claim. Remember, if this is true, that has to be true. If this is false, then that has to be false. That's what if and only if means. Now, the one big thing I really want to emphasize here is that in very many of our proofs, we often performed induction and proved it to both directions via induction. What I'm going to do is, sometimes it's helpful to split these into the two parts separately, the if-then part and the only, and then the, like I have if-then, and then I have if-then, like this. I like to think of it like that in terms of two directions. If I prove them separately using induction, then most certainly that will satisfy this claim, because that's just the same thing as saying this. So I'm going to do that here because I want to try to pick up and prove it using different aspects of the things we're talking about. One, if I'm picking up a string from this language, I might do perform induction on the length of the string because I already know that this is a palindromic string. It's a palindrome. However, over here, the language's definition isn't really one that makes it really easy to do that. Instead, because remember, it might replace multiple symbols, right? It doesn't just replace like one symbol or read one symbol like we had with DFAs, for example. It might replace several of them. So in this case, we might want to use perform induction in a somewhat different way, as I described previously. So we prove that GP is correct. So we're going to try proving that. That is, the language of GP is the language of all binary palindromes. That says palindromes, by the way. It's sort of melted. You know when you make a really good grilled cheese sandwich and the cheese kind of drips off the sides like this? That's what happened to this. This says palindromes right here. So here we go. Let's prove this. So I'm going to prove the two parts separately, and I'm going to use our notation for reversal to help me describe palindromes. So we prove the claim using mathematical induction. So using induction, that W is in the language of GP if and only if W is equal to W reverse, or W reversal. So W with the R, that just simply means take the string, reverse it, make it backwards, which that's exactly what a palindrome is. So to prove the claim, we perform induction on the number of substitutions or rules so how many times I apply the production rules used in a derivation. So I thought I would start off with this because we haven't done any examples like this up to this point for context-free languages. Or really just generally, we haven't played around with grammars enough. So we're going to perform induction on the number of substitution or production rules applied. You might, as I said previously, the reason why we might go about it this way as opposed to on the length of the string is because, remember, when I apply production rules, just say like this one, notice that when I apply a rule, it might introduce more symbols, elongating the string by more than one symbol, right? So performing induction on the length of the string may not be a correct approach here. It might not. It's at least not an intuitive way of going about it. So what I'm going to do here is I'm going to prove the parts separately. So namely, this is going to be this direction. So if I start off with a string that is a part of this language, let L of GP, then it is a palindrome. I'm going to try proving that to you. So we're going to prove that part of the claim, and then we'll prove the other part of the claim. That is, if I give you a palindrome over the binary alphabet, then it is in fact one that gets generated by this grammar. So does everybody understand the game plan? I'm going to prove each part separately. The first part, the one I'm going to establish here, where I take a string from here, I show you that it actually is a palindrome. But I'm going to have to do that with, I'm going to do that over, because remember, W is any binary string, right? So I'm going to perform induction on the number of substitutions or rules so that I can capture all possible strings that can be produced and hence belong to this language. So actually, one thing before I get into this, I just want to remind you that if W is in the language of GP, so please remember, the goal here is that if this is true, then that means by definition that, and this is why I'm going about it this way, is that I start off with the start symbol, A here, and I eventually end up with W. So I know W is a part of this language. I would like to establish that W is W reverse. That's what we're trying to do. So notice that the definition requires me to apply some number of production rules to get the derivation. So we're going to start off with the base step. So what does that mean? That means I have to apply, because remember, I start off with a variable. I need to get a terminal, so it means I have to apply at least one rule. So that means I start off with one rule. If one rule is applied, it results in one of, so which of these production rules gives me a terminal string? That one definitely doesn't, right? I would need to apply more rules. Same with this one. It's these three here. These all end up with terminal strings. But each one of them is a palindrome, correct? It results in one of A derives 0, A derives 1, or A derives the empty string. These are all palindromes, right? These are all palindromes, completing the base step. Now the fun begins. Now we got to perform induction. Now, at first you might say, Dan, this sounds really scary. It's spooky, spooky, spooky skeletons. Because now you're imagining I'm at some step of deriving a string. So I end up with some potential form. And now what I need to do is I need to show you that when I apply the next step, I end up with a string that's in, that is indeed a part of L of GP, that it is a palindrome. So I'm starting at an arbitrary step. But I assure you, it's not that scary because of the recursive nature of these grammars. So fix sum n greater or equal to 1. Assume, so I'm gonna come up with an induction hypothesis here. So assume that all derivations with n substitutions are binary palindromes. I'll just say palindromes just for brevity. So that's the induction hypothesis. We show that any derivation that performs n plus 1 substitutions, n plus 1 substitutions results in a palindrome W. So I'm going to imagine because remember, I've proved this for one rule, right? So I'm going to now consider and suppose that for some n, that it indeed derives a palindrome. So now what I do is I want to consider when now we have to perform n plus 1 many derivations, or substitutions, to be a bit more precise with my language. So if you're looking at this and saying, oh, well, surely there's some nice property that this grammar actually has. So please note that n plus 1, because n is at least 1, when I add 1 to it, it has to be more than 1, correct? Strictly greater than 1. As n plus 1 is strictly greater than 1, observe that such a derivation consists of applying at least 2 production rules. Now, if you keep this in mind now, you imagine you have this parse tree. It means that when you apply the production rule, you end up with, you have to have more than one internal node, right? You can't just simply go, okay, start symbol, boom, all terminals for the leaves. It has to be that there is an actual intermediary step that gets you to terminal string. So you most certainly know right away, based on this observation, that there's going to have to be at least 2 production rules used to get to the terminal string. Which ones can I use then? Which one must be used? Is there more than one that has to be used? Or can be used? I should use, maybe can might be the appropriate word. You know right away it's not this one, right? It's not that one. Because that one requires, this will get you right to a terminal string. Same with this one, same with that one. So you know it's either going to be this one or that one that gets used. That's going to be the one that you start off with for the production rule. Notice that the way this is designed, it forces us to pick either one of those production rules. It has to be one of those 2 in the induction step because of how many production rules we have to use. So, and the only production rules whose bodies have variables, right? Because if it has a variable, then you most certainly don't have a sentence or terminal string. Have variables, or variables in general, are either A produces A0, 0A0, or A produces 1A1, right? Those are your only 2 options. So now this is where the induction hypothesis becomes our best friend. So by the induction hypothesis, any derivation of n substitutions is a palindrome, X. So think about it. We have to perform at least one production rule. It has to be one of these 2. It has to be. But the induction hypothesis tells us that if you perform n substitutions, you get a palindrome. Very interesting, right? It's almost like you just kind of like, it's like put a little cherry on top. So check this out. Implying A derives, with the star there, derives x, and x equals x reverse. Palindrome, right? In any case, so watch how I use x here. In any case, A, it transforms or gets changed into 0A0, which of course produces 0x0, which this equals 0x reverse 0, right? And remember, is this a palindrome right here? That's a palindrome, right? Like this is a palindrome. This has to be. Like this has to hold. So 0x0 is a palindrome because of the induction hypothesis, because we know x is x reversal, and we just appended zeros on both sides, right? Remember, think of it like the little wave when I was designing the grammar. And I derive from A, I get 1A1, which derives 1x1, which of course is equal to 1. I'm just going to use ones like this. Otherwise it looks a little bit like cardinality, and I don't want to really confuse you in that regard. Resulting in a palindrome for W. So do you notice here that when I do the induction step, I'm taking advantage of the fact that it's almost like you're layering the extra step on top of the underlying structure that guarantees the palindrome. So I'm just showing you how to get to x, which x is coming from providing the previous number of substitutions. So do you see how with an arbitrary number now, if you apply the principle of mathematical induction on the number of substitutions, that this indeed qualifies for that one direction of the proof. Therefore, by principle of mathematical induction, if W is an L of GP, then W is equal to W reverse. It's a palindrome. So that completes one direction of the proof. Now we got to prove the other direction. Now the other direction will feel a little bit more conventional. It'll be a little bit more conventional, but I'm going to be making, I'm not going to be using weak induction. I'm going to use strong induction implicitly. So for those that are really technical with these things, the reasoning is not terribly scary or anything like that. It's just a little bit more subtle. Now let's prove the other direction. That means if I'm given a palindrome over the binary alphabet, then it has to be a string that is a part of the language of our context-free grammar GP. If W satisfies W is equal to W reverse, we show via induction on the length of the string W, how to derive W using production rules of GP. So you're going to see it's a little different, because now remember the way I generate strings is by applying the production rule. So I got to show you how that's done. And it's going to depend on the length of the string. So let's start off with the base step. So I'm going to have two base steps. I'm going to start off with when the length of the string is 0. And then I'll do length of string is 1. Then we'll perform the induction step. Well, when the length of the string is 0, then we know it's already the empty string, right? So which one can I use? Well, it was the rule with epsilon, right? The only applicable rule is A produces epsilon, so A derives epsilon. So what I'm going to do is I'm going to show you how you derive W using the production rules. So now let's consider the base step when the length of the string is 1. This reasoning is going to be nearly identical. It's just now it's just going to be with 1 or 0, right? Those are the only possible palindromes with length 1. As the length of the string is 1, either W is 0 or W is equal to 1. The only production rules that generate strings of length 1 are A produces 0 and A produces 1. And as expected, of course, A derives W. So far we got strings of length 0, strings of length 1. Now, I'm going to do something fairly careful. So watch this carefully, okay? So I'm going to apply it from 1 higher, and I'm going to assume 1 lower, okay? 1 or more lower. I should be a bit more precise about that. So in the induction step, I'm going to carefully start with a given step, and I'm going to show you from previous steps how to get what we're trying to establish. So we're going to fix some length of the string to be 2 or more. So that means by definition, either W is going to look like 0x0, or W is going to be 1x1, where the length of x is going to be it's going to be 0, somewhere between 0 inclusively up to n minus 2. So what I'm going to do for our induction hypothesis is I'm going to assume that A derives X holds. So you might ask, Dan, why are we doing it this way? So I'm starting up here and I'm working my way down. So the thing is, I don't know what X looks like in terms of its length, but I'm going to presume that it's going to be any one that is going to be shorter than ours. But based on the structure of this, I can know that I can take away 2 of the symbols, meaning it's always going to be that this X is going to be a shorter string. Then one can derive can derive W in each possibility. Using the induction hypothesis. So now we're going to break it into cases. So let's head over here. So we have two cases, right? We already identified the form of what W might look like. Like it has to look like one of these two. So in the case that W looks like this, well, look at this. By the induction hypothesis, I can apply a production rule to get 0x0. Because what do I end up with? So technically speaking, it should be that we derive this because x is a whole bunch of these. Remember, this is in fact going to be a terminal string, which this is in fact W, right? So this is our W in question in this case. Now suppose that W is 1x1. Just to make it a little bit clear, let me add a step in here, just to make it a little clearer where we're getting this from, because I think it's a little helpful to see it. There we go. I think that's a little better. So I'm applying the production rule to get 0A0, and then I through a sequence of steps, because I know that A derives X, that I should get this as a result. And that's W. So we do the same thing here. And by the induction hypothesis, I can replace A with X, which that's just W, which completes the induction step. Therefore, I can apply the principle of mathematical induction now. Hence, by the principle of mathematical induction, if W is equal to W reverse, i.e. it's a palindrome, then W is in the language of GP. So I showed you how to get a string of that given length. And that completes the proof. Because I've already established that we're proving both directions. Now that I've proved both directions, this establishes the if and only if claim that satisfies our definition for the language of the context-free grammar.